So we've begun building our propositional logic, our precise logical language that's built out of sentences. And so far it's not very interesting, is it? Because we have sentences, but they're just atomic sentences. So the most we can do with this logical language is write down P, Q, R, some atomic sentences. There are, though, when we look at a natural language like English, which we're taking as our guide, as we said, to help us build more complexity into the language, there are more complex sentences that we might want to try to understand. And here I've picked a couple examples. Look at this sentence. If wood is less dense than water, then wood floats on water. And here's another sentence. Iron is not less dense than water. What's interesting about the sentences is that this one is obviously not atomic, right? If I cut out this part right here, I get a sentence. Wood is less dense than water. So that's atomic, it seems to me, maybe. But it's inside this sentence. It's a complex sentence with parts that are sentences. And it seems, this also appears to be a sentence, that these two sentences are related by this thing, if then. So it would be helpful in our logical language if we could take sentences like this, more complex sentences, and be able to represent them. As we'll see later, that's actually the most powerful thing we can do, because that's going to allow us to finally study arguments. But in any case, just even looking at it, I would think, well, how does that work? What's this if-then doing? I'd like to get into it. Similarly, here, this sentence, let's set this one aside. We'll talk about it in a little bit. But it's sort of interesting, isn't it? I'm not sure if it's atomic or not, just glancing at it. But this not seems to be doing something to the sentence. And so we should think about, what is that not doing? And can we analyze that also? So let's analyze both these things, both if-then and not. We'll start, as I said, with the if-then sentence. Well, in our propositional logic, we said the smallest element of our logical language are going to be atomic sentences. So you can imagine me making a translation key for this, right? And ideally, it would be great if we have in our translation key the elements of our atomic language that are, of our propositional logic that are atomic sentences. I could name this, just P, as we were saying before. You can assign atomic sentences in our logical language just a single letter, and that sort of is our way of saying, hey, this is the smallest element of our atomic language, and it's either true or false, right? And I could do that here. I could just call that P, but that seems a bad idea, because it would be hiding. It would be, first of all, it suggests that this is atomic, and it's not. And it would hide what's going on in here, that there's two sentences in here, that these sentences are being related by this if-then thing. So we would like to avoid treating a complex sentence like this as if it were atomic. So what we ought to do in our key, it seems then, is if I put over here my logic, and I put over here my English, I ought to assign, an atomic sentence in my logical language like P to the parts of this that are atomic. So wood is less dense than water. And this other part, wood floats on water, similarly, that seems to be atomic. I don't see any part of that is itself a sentence. And so we ought to give that an equivalent single letter in our propositional logical language. There has its meaning here translated for us in our translation key as wood floats on water as this atomic sentence. With this translation key, it seems now I could actually sort of capture some of what's going on in this sentence. I can say, hey, this sentence is saying that if P is true, then Q. Now that's actually a mix of English and logic, right? That's a mix of English and logic. I use English for the if then, and I use my logical language for P and Q. Now, jokingly, I said logicians are lazy. We want to have like a single letter instead of writing all those letters for a whole sentence. But I'm just joking, really, because there's a point to having a single letter here, as we said, because it's drawing our attention to this is the smallest element of our logical language. It's either true or false. Similarly, do we really want to write out if then? We could, but it seems what we're really talking about is one kind of relationship. And so what would be better for us in our logical language is if we introduce a symbol for this relationship, and now and then we could precisely define that symbol. And in that way, we wouldn't, we would be escaping any ambiguity, we'd be avoiding any vagueness, because we would have our own special symbol which we define precisely. And so that's what we'll do in our logical language. We'll say, instead of writing if then, we're going to use arrow. And we're going to put parentheses on the outside of that. So what we'll do is when we see one of these sentences that says if then in it, right? If wood is less dense than water, then wood floats on water. First, what we want to do is we want to create a key which translates from our logic to the equivalent in English so that we know what the atomic parts are in our logical language. And then we're going to treat this if-then as some kind of relationship between those sentences, which we'll just represent with an arrow. Now, here's an interesting fact. We've got to ask ourselves, okay, that's interesting. We've got a way of writing that, but what does it mean? And that's the important point. Whenever we're going to add something new to our logical language, we really have to back up and say, okay, how do we add it? How do we write this out? And what does it mean? And those two questions, how do we write it out and what does it mean, have to be our next topic. And it's a very important issue in logic. It's the issue of what we call syntax and semantics. So we've started doing something new. We want to explore how we could represent in our propositional logic more complex sentences. And to do that, we introduced a symbol for if-then. Now, it's traditional logic to call an if-then sentence a conditional. So that's a nice phrase, hopefully not too complex, but it's really just another word for these kind of if-then sentences, right? And we gave an example last time of two atomic sentences related with this arrow, which we're calling now the conditional. We also have other names for the parts. This is called the antecedent of the conditional. The if part, sometimes you might call it. That's called the antecedent. And the then part is called the consequent. That's sometimes useful terminology to have. We've added this thing to our logical language. We said sometimes I see in English a phrase if, then, and I want to capture it. Well, I'll capture it with this arrow. However, that's not really telling us much, is it? Because I want to know what it means. And I want to know when can I write it and how can I write it. And this really raises this question of a fundamental concept in our logic, which it wasn't convenient to introduce before now, but now it is convenient to introduce it, and that is this fundamental distinction, two related but different concepts that we're going to use throughout our study of logic: syntax and semantics. Now, syntax is about how do you correctly write something. It's rules about strings of symbols, basically. How can you correctly put those symbols together? What's an incorrect way to put those symbols together? So, for example, the syntax we've already sort of introduced on the sly. We said that if we have two sentences like P and Q, and if you put an arrow between them and you put parentheses on the outside, you get another sentence. Now it's a complex sentence. It's no longer atomic. We'll say that again in a minute in a more formal way. But we're going to need a third concept before we do that. So we'll come back to that. Also, what does it mean? Syntax, as I said, is about shape. It's about what kinds of strings of symbols are allowed. But we also want to know, well, what the heck does a symbol mean, right? I've said something here. What did I say? What's it mean? That's semantics. Semantics is about meaning. Syntax is about writing. It's about the strings of symbols. When are you allowed to write certain strings of symbols? What are the right order of the symbols and so on. Semantics is just about what does it mean? What does it mean? Now, for us, the semantics of our propositional logic, because it's about propositions, it's built out of propositions, our semantics is really just about truth and falsity. So in other words, if we want to know the semantics of this, what we will ask is, when is it true and when is it false? That's what we're going to ask, okay? So what we need to do is specify in some way the truth value of this sentence in terms of its parts. I don't really know the truth value of the parts. I may, but I may not. In a way, I ought to be able to make these conditional sentences, these if-then sentences, out of other sentences where perhaps I don't know the truth value. I know it's either true or false because of our bivalence principle, but what if I don't know? What I really want is an explanation of when this thing is true in terms of the possible truth values of its parts. So that introduces an interesting tool that we're going to use throughout our study of logic to express semantics. Here I've got two atomic sentences, right? And they're related by this arrow. So if you think about it, there's several different ways this could go. These could both be true, and then I could say, well, what does it mean to put an arrow between two true sentences? They could both be false. This one could be true and that one could be false, or this one could be true and that one could be false, right? So I actually have 4 possible combinations. And so we would like to capture that somehow. And there's a way we do that. We make what is called a truth table. And what we do is we draw a line, and I write over here the parts of my symbol, right? Here that I want to define, the arrow. And in this case, it's got 2 parts, right? P and Q. And as we said before, I got to consider all the possible ways. If I'm going to really say what this arrow thing means, I've got to consider all the possible meanings, right? That these can have. And in our propositional logic, that really just comes down to whether they're true or false. So I got to consider the case of when they're both true, or the other possible truth value combinations. The best way to think about this is to think, for a sentence like Q, it could be true or false. But it could be true or false when P is true, or it could be true and false when P is false. So now each row here is a kind of way the world could be. The world could be such that they're both true. It could be such that P is true or Q is false. It could be such that P is false and Q is true. Or it could be such that they're both false. And there's 4 kinds of ways the world could be that matter to me. Remember, each sentence in our logical language is either true or false, never both, never neither. So I just have to consider the possible combinations. And when we make one of these truth tables, what we do is we put over here all the possible truth values. All the possible truth values of the parts. There's 2 here. And then over here, we're going to define, we're using a truth table here to define the semantics of arrow. Now, this, I must confess, troubles a lot of people because we generally have agreement about the first 2 rows. If I say to you, if P, then Q, and it turns out, in fact, that P is true, and it turns out, in fact, that Q is true, it seems I said something true. We could set aside our example. Maybe, imagine we start a new logical language. Our example was about wood and floating, right? Imagine we start a new logical language. It's about promises. And I say to you, if you give me $50, then I will buy you a ticket to the concert. Because maybe the tickets are going on sale in a while, and I'm going to go and buy tickets for all my friends. So imagine you do give me $50, and imagine I do buy you a ticket to the concert. It seems I kept my promise, doesn't it? It seems that I spoke the truth when I said it, or I spoke sincerely. What if you give me $50 and I don't buy you a ticket? It seems I spoke insincerely, right? That seems easy. It seems it's false. However, what about these other cases? Well, it's funny, in a natural language like English, you might think, well, we don't talk like that, you know. We don't say if then in situations where the first part, what we call the antecedent, isn't true. We're not interested in that. But remember our principle of bivalence. It's absolutely essential, according to our principle of bivalence, that every sentence of our logical language be either true or false, never both, never neither. So we can't have a nothing here. We can't have blanks. The world might be like this, and the sentence cannot be undefined for that. It has to have a truth value. Given that, most logicians feel strongly that it should be true, that we should have true here. Now, let me try and convince you of that. Go back to my example, you know, and we're wondering whether I'm being sincere. Whether I'm speaking sincerely when I say this. I say to you, if you give me $50, then I'll buy you a ticket to the concert. You don't give me the $50, I buy you a ticket anyways because I'm a nice person. It seems like you shouldn't think I was being insincere when I made my promise, you know. So it would be strange to say, well, you were lying when you made that promise. You didn't mean it or something like that. That would be strange, it seems to me. So we're going to call that true. Similarly, if you didn't give me the money and I didn't buy you a ticket, it doesn't seem that I was being insincere when I made my promise. So that seems best defined as true also. You can think of other examples. Try it for yourself in which we have an if-then, and consider those cases where the first part, the antecedent, the if part is false, and think about how the sentence looks to you. In some sentences, it's just going to seem kind of funny and maybe it doesn't seem well defined, but there's going to be other sentences where it seems to me you'll agree this is probably the best translation. And it really does seem that we shouldn't put false in there. And given that, this seems the best truth table we could have. So this right here is what we call a truth table, and it is defining, it is giving you the semantics of this connective, what we call a connective, this symbol, the arrow. We call those a truth functional connective in logic. Why connective? Because it connects other sentences. Why truth functional? Because its meaning is a function of the truth of its parts. A function is a kind of process where you put a certain number of things in and you get always exactly one thing out. So here we put in two truth values and we got exactly one out. Right? So this is what we call a truth functional connective. You don't really need to know that, but you do need to memorize this. You have to memorize the meaning of if-then. If you don't, you'll be confused throughout our studies as we look at this. Now, there's a wrinkle here, which we're going to have to handle. I know it's hard because we're introducing a lot of new concepts. We've introduced syntax, we've introduced semantics, and now I'm going to introduce a third new idea. But we have to do it. Here, this isn't really a good definition because it's talking about particular sentences, P and Q. What if I have R and S? What if I have different sentences? What if in here I don't have a atomic sentence, but I have a complex sentence? And so on, right? So it really isn't a good definition unless it's somehow I'm able to generalize it. And the way we do that is we're going to introduce something like a variable, but it's a variable for sentences. And we have a fancy name for that in our logic. We call that the metalanguage. Meta, here meaning is ancient Greek for after, and we use it sometimes to mean at a higher level. And this is sort of language at a higher level. It's the language about our language. And to signal that we're doing the metalanguage, we'll use Greek letters. So what we could do is we could replace these with Greek letters. And we could say, here we go, right? Phi is any sentence, psi is any sentence, and phi arrow psi is our conditional made out of combining them using this if-then, this special symbol we have for if-then with the parentheses on the outside. And now, this is a good definition of the meaning of the arrow, of the meaning of the conditional, of the meaning of if-then, as far as we're concerned in our logical language. Because what we've done here is we've defined it for any two sentences, phi and psi. That's the idea. Not just particular sentence P and particular sentence Q. For any two sentences, phi and psi, if they're both true, then phi arrow psi is true. If phi is true and psi is false, then phi arrow psi is false, and so on. So that's our concept of the meta language. Sometimes we're going to want a variable that means any sentence. We'll use a Greek letter, and we switch then to our logic about logic, our meta language. This idea allows us, I promised a little bit ago, that we would have a more formal notion of the syntax, so we can do that now. But first, just briefly, remind ourselves, this is our semantics for the conditional. Right? This is our semantics. We actually define the semantics using this special table, which we call a truth table. We're going to use these truth tables in two other ways later in the semester, or excuse me, later in the class. But for now, it's enough to just use them only in this one way, using them to define the meaning of a connective, define the meaning of something that allows us to make more complex sentences. So this table is actually a definition. It's a definition. And like all definitions, we didn't discover it, we didn't, find it through scientific method or something. We stipulated it. And the important thing is that you and I talk this way for the rest of the semester. Whenever we write down arrow, we mean this. Okay? As I promised, now that we have this idea of the meta language, we can also more precisely define the syntax for the conditional, or for, if you prefer, the arrow, right? And the way we'll do that is we'll simply say, if phi and psi are sentences, then parentheses phi arrow psi parentheses is a sentence. Very simple. The syntax of the propositional logic is always easy. But we need to say this. We need to say it precisely at least once. And this does tell us something. It tells us the arrow goes between two sentences. If you put the arrow in front of them, it wouldn't be right. If you didn't add the parentheses, it wouldn't be right. So it is actually making a distinction between other possible ways we could arrange these symbols. Think of all the different ways you could arrange those symbols. Those would be different syntaxes. But this is the only correct one for the conditional. If phi and psi are sentences, then parentheses phi, arrow psi, parentheses is a sentence. Note that phi and psi could be a complicated sentence. So this doesn't have to be atomic sentence, arrow, atomic sentence. It could be some enormously complicated sentence, arrow, enormously complicated sentence. We haven't seen any very complex sentences yet, but maybe we will soon. And again, this uses our meta language, our idea of the meta language, to define the syntax, this time, for the arrow. Throughout our study of logic, we're going to constantly go back to the idea of syntax and semantics and how they're different, and also we want them to interrelate. We want them in some ways to mirror each other in deep ways and in interesting ways. That's an enormously interesting topic, and we'll talk about that quite a few times over the semester. But for now, just remember, syntax is about what kinds of strings of symbols are allowed, what am I permitted to write, and semantics is about once I write down a syntactically correct string of symbols, what does it mean? Basically, when is it true, when is it false? Okay. So we've introduced the idea of more complex sentences and adding more complex sentences to our propositional logic, not just having atomic sentences, but we saw with the conditional, now we could have if-then sentences, and we know how to write them and we know what they mean. We also had an example that we looked at of a sentence that had a not in it. Now when you look at this sentence, you might think it's atomic because there's no way to cut it and get out a sentence, right? There's no way I can draw a line and say, cut it here, less dense than water. That's not a sentence. Or it is not. That's not a sentence, right? But here's a suggestion. We logicians think that this is actually shorthand in English for something else. we think it could be treated as equivalent to, it is not the case iron is less dense than water. If you are willing to agree with me, and to agree with all the other logicians, that these two sentences are equivalent, they mean the same thing, then we could think of this sentence as being sort of shorthand for this one. And in that case, you look at this, I think you'll agree with me, it is perhaps not atomic because it contains a part that is an atomic sentence. Namely, if you and I cut it here, we're going to get, it is not the case that, this thing, it's not a sentence, but it's something. And we're going to get this other thing, an atomic sentence. Iron is less dense than water. So we could make the case that this sentence is not atomic. It has a part, iron is less dense than water, which is atomic, and then it's got this other thing, not, or it is not the case that. So what we'd love to do is be able to capture that also in our logical language. So we didn't just have conditionals, but we also had conditionals and these kinds of sentences. Okay. What we've done up to now, though, is we've introduced this idea that whenever we add something to our logical language, we better say, what's the syntax? That is, how am I allowed to write it? And we better say, what's the semantics? That is, what does it mean? So you and I should turn next to that. What is the syntax and semantics of this thing? It is not the case that. Okay, we want to add this new thing to our logical language so that we have it to go along with the atomic sentences and with the arrow, which is going to allow us to express what we call conditional. And this new thing we'll add we'll call negation. Kind of an obvious name, isn't it? And what we're trying to capture is this thing. It is not the case that. Now, if I was making a translation key, as we've typically done, I would capture this atomic sentence, right, with my logic. I think we had, up to this point, used P and Q, so I will use R, and I would capture this English sentence. I would say, in my logical language, I have a symbol that stands for the atomic sentence. Iron is less dense than water. Liquid water. And I would capture it in this way, right? I would say, whenever you see this R, you know that's an atomic sentence. And if you were to ask me what's it mean, I would say, well, if you want to know what it means in English, my translation key will tell you it means iron is less dense than water. So we need, as I said, we could write it is not the case that R, but as you already see the pattern here, logicians, we like to introduce a symbol that captures it and gives us like a way to say, hey, this is a formal piece of our logic now. We're going to define it precisely, and it's going to be a new element to our logical language. So what we traditionally use for it is not the case that is this symbol, like a little bar with a slight down tick at the end. Yes? And so we would translate this now as not R. We would read that as not R, or it is not the case that R. Very simple, right? We have any sentence. I can say it is not the case by putting a little, what we call a negation in front of it, this line with a little down tick at the end. That's the negation symbol. What we have to do now, always, when we say something like that, is say, what's the syntax? What's the semantics? And we need to do that using our metalanguage, so we say it in a very general way. So now we'll use Greek letters, which are going to be like variables for sentences for us. And we know we switch to our metalanguage. We switch to our logic about logic, our language to talk about our language. And we can say, if phi is a sentence, and so remember phi is any sentence, then not phi, we can just read that not, is a sentence. Pretty straightforward, but it is a rule because it tells us, for example, that you don't write the sentence and follow it with the not. You put the not or the negation before the sentence. So it does restrict how we are combining these symbols. Again, syntax is always about what symbols you have and how you combine them, right? It's a rule about the strings that you can write, the strings of symbols, and which strings of symbols are permitted and which aren't. This is permitted. Take any sentence and you put a not in front of it, that is a sentence. We had the syntax for the negation now. Take any sentence phi, if you put the negation symbol in front of it, you get a new sentence. But what does that mean? That's the question for semantics. If our syntax tells us you put a negation in front of it, one sentence, then the semantics is going to be a relationship really to that one sentence. Each sentence in our logical language, principle of bivalence, is either true or false. We just have one sentence here we're talking about, so we just have two cases that we have to consider. It could be either true or false. Well, what do you think the negation should mean? Almost everybody agrees on this. If I have a sentence which is true and I tell you it's not the case, it seems I've said something false, doesn't it? On the other hand, if I have a sentence that's false and I deny it, I say, no, that's not right. It seems I said something true. And there's the semantics for the negation. Pretty easy to emulate English, pretty easy to reason it out from our understanding of English. And our negation has a very clear meaning now. It's given right here. So from now on, whenever we write this symbol, we know exactly what it means. If you put it in front of a true sentence, you said something false. If you put it in front of a false sentence, you've got something true. Because we've written this in our metalanguage, this is a general claim about every sentence in our logical language. It can be useful to point out to you that there are alternative symbols that logicians sometimes use. You don't really need to know that. But in case you're someone who goes out of curiosity and looks at a different logic textbook, you might wonder, what are these other symbols here? I've never seen them before. Often, they're just alternative symbols for the same ideas we've already introduced. And the syntax is very similar, and the semantics are identical. So here's an example. The most common alternative to the arrow for the conditional is to use this symbol, which is sometimes called the horseshoe. And the syntax, as you can see, is very similar. If phi and psi are sentences, then parentheses phi, horseshoe, psi, parentheses is a sentence. Pretty much the exact same syntax, except that we replace this symbol. The truth table would be the same. The semantics is identical. Logicians do not use difference in semantics for the conditional. We all agree and use the same semantics. Same for the negation. The most commonly used alternative symbol for negation is a tilde, like this. And typically the syntax is the same. It's just put the tilde before a symbol and you get a sentence, right? Put the tilde before a sentence and you get a sentence. Some logical systems will also require in the syntax that there are parentheses on the outside. So the syntax would be parentheses, tilde, sentence, parentheses. So if phi is a sentence, then parentheses, tilde, phi, parentheses is a sentence. And finally, in some very old logic textbooks, they use a bar over a sentence to mean the denial, right? That's a pretty bad syntax use, frankly, because it's then hard to have several negations. It's very confusing to the eye, but that was done sometimes in older logic textbooks. So in all three cases, the semantics would be the same. If you put this bar over phi, you've changed its truth value. If phi is true, then that sentence would be false. Instead, if phi was false, then by putting a bar over it, I would have said something true, and so on. Again, you don't need to know that, but you might be curious because if you want to reach out and read other logic textbooks, you'll want to know that these things are the same in terms of their semantics and nearly the same in terms of their syntax.